We choose to go to the moon in this decade and do the other things. Not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Getting my feet out. Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh? When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Listen, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 115 of the Space Rocket History Podcast. And now, Apollo Little Joe 2. You may recall episode 19, titled Little Joe Mercury's Test Vehicle. That was Little Joe 1. It was used to qualify the Mercury Launch Escape System. This episode is about its successor, the Little Joe 2. Little Joe 2 was an enlarged version of the Little Joe concept, and it was used to test the Apollo Capsule Launch Escape System. The vehicle was designed by General Dynamics. Early in the Command Module contract, North American Aviation and Houston engineers had agreed on a flight test program putting boilerplate command and service modules through structural test and checking out the abort-escape system. In mid-1961, while he was still with NASA before joining North American, Alan Collette suggested using a fin-stabilized cluster rocket solid propellant booster for these tests, called the Little Joe 2. It would be able to propel a full-size Apollo re-entry spacecraft to velocities as great as those in the critical portions of the Saturn trajectory and to altitudes of 200,000 feet. The test would be a simple and fairly inexpensive way of determining in flight the full-scale spacecraft configuration concepts, systems performance, and structural integrity. Test of the launch escape system at maximum dynamic pressure would be the most important. Launch sites for Little Joe were considered at Wallops Island, where Little Joe 1 was launched, Elgin Air Force Base, Florida, and the Cape. But the New Mexico desert north of El Paso, Texas, was selected early in the spring of 1962 as the Little Joe 2 test area. The Army's White Sands Missile Range seemed the most suitable for Little Joe 2's ballistic flight. All of the unmanned launch escape qualification flight tests using the Little Joe 2 booster were conducted at the White Sands Missile Range in New Mexico between August 28, 1963 and January 20, 1966. NASA engineers expected to conduct three kinds of tests at White Sands. First, pad aborts, in which a solid fuel rocket mounted on a tower attached to the top of the command module would pull the spacecraft away as it would have to do if the Saturn threatened to blow up on the launch pad. Second condition, maximum dynamic pressure, also known as max-Q, test in which the rocket would pull the spacecraft away from the launch vehicle if the booster veered off course shortly after launch. And the third method, high-altitude test, in which the rocket would haul the spacecraft away from the launch vehicle if the Saturn were unable to boost its payload to orbital flight. And surprisingly, leaders also expected to flight test the lunar module in New Mexico using the Little Joe 2 booster. Little Joe 2 was 95 feet tall and 13 feet in diameter, so the name Little Joe is a little deceiving. It is only little when compared to a Saturn V moon rocket, which is 396 feet long. It's actually 3 feet larger in diameter and almost as high as the first manned space vehicle, the Mercury Atlas, used to put John Glenn, Scott Carpenter, Wally Schirra, and Gordon Cooper in Earth orbit. Now, the Little Joe's propulsion was a solid rocket booster designed and produced by Convair Division of General Dynamics for the Apollo program. The Little Joe 2 used a cluster of up to 7 Algol 1D solid propellant motors, which produced a combined total thrust of 860 pounds. At the time, it was the most powerful solid propellant rocket ever flown in the U.S. Little Joe 2 was highly versatile in that various combinations of the Algol and the Recruit TE-29 solid rocket motors could be used in different firing sequences to provide an optimum thrust combination for a wide variety of missions. Now let's consider the structure of the Little Joe 2. The structural shell that supported the Apollo payload and housed the solid rocket motors was a simple corrugated aluminum cylinder which was stiffened by ring-shaped frames. This shell consisted of 2 sections. The lower section provided the primary structural support for the motors and aerodynamic fins, and the forward section provided support for the payload and flight control electronic systems. It also locked the motor in place at the top. The basic structural element of the vehicle was a large built-up thrust bulkhead at the base of the booster. The bulkhead transmitted the thrust forces from the rocket motors uniformly through the corrugated shell. The aerodynamic fins were attached to the aft section of the bulkheads by 3 bolts to provide easy on-site assembly. Moving on to flight control. The first 2 Little Joe 2 test flights did not require precise altitude control and so were conducted with simple fixed fins. All other tests used fins with controllable elevons. The aerodynamic control that could be generated by deflecting the elevons was directly related to available aerodynamic pressure. At any given altitude, the faster the rocket moved, the higher the aerodynamic pressure. However, as a rocket ascends, the air gradually thins out until the rocket reaches altitudes where there's no air at all, and therefore no aerodynamic control force, no matter how fast the rocket is traveling. Consequently, on a high-altitude rocket flight, the aerodynamic pressure increases from 0, reaches a peak, and then decreases to 0. For this reason, a reaction control system is required for initial guidance during liftoff and again at high altitudes. At the risk of repeating myself, I want to say that it is important to understand that the maximum aerodynamic pressure condition is one of the most critical factors in determining the structural strength requirements of a rocket. One of the jobs of the Apollo Little Joe 2 test was to simulate a Saturn V flight which might fail at this critical condition. Moving on to guidance. The guidance system controls the flight attitude of the Apollo Little Joe 2 according to a pre-programmed schedule or as commanded by radio from a ground station. This equipment was located in the forward section of the structural shell. Electrical command signals pass from the guidance system to the fin control surface actuators and reaction control system via wires on the outside of the shell, which were covered by a fairing. Each fin included a pneumatic hydraulic system that actuated a corresponding aerodynamic control surface in response to guidance system command signals. Now, on the later flights, a hydrogen peroxide-fueled reaction control system was installed on each of the fins in order to provide for attitude control. Gaseous nitrogen provided fuel pressurization and operated the motor valves. A catalyst in the decomposition chamber of each reaction motor converted the hydrogen peroxide to oxygen and superheated steam, providing 600 pounds of thrust from the motor jet nozzle. The motors were mounted in back-to-back pairs that thrust perpendicular to the fin plane. The system provided thrust pulses in response to command signals from the guidance system. Now, moving on to the launch escape system. The launch escape system would take the command module containing the astronauts away from the Saturn launch vehicle in case of an emergency on the pad or until 173 seconds after liftoff. The launch vehicle emergency detection system was designed to warn the astronauts and automatically initiate the abort signal. Also, a manual abort could be initiated before or during launch by the command pilot. After receiving an abort signal, the command module service module separation device was detonated and the launch escape and pitch control motors were ignited. The launch escape motor carried the command module to a sufficient height so that the Earth landing system could operate, while the pitch control motor simultaneously pushed to the side so that the command module would be carried away from any debris. Now, a few details on how that worked. On the top of the escape tower, there was a 1-foot-high instrument called the cue ball. The cue ball took air pressure readings from 8 little holes drilled in a ring around the nose. The pressure in all holes would be equal only if the rocket was flying absolutely straight. Any drift would create a pressure difference, and that would read out on a gauge in the cockpit. If the astronauts didn't like what they were seeing, they could hit the abort switch, and a millisecond later, 3 small explosions would drive guillotine blades through the tie rods holding the command module. The main escape motor would fire, and a small rocket mounted sideways in the tower would steer the capsule out of the way of the booster's flight path. 11 seconds later, a pair of fins would pop out near the top of the tower, and, like feathers on an arrow, they would swing the capsule around so the blunt base of the cone was forward for a landing. 3 seconds later, explosive bolts at the base of the escape rocket would free it from the command module, and a third and final rocket motor would pull the tower away. During a normal, safe mission, the launch escape system was jettisoned using the tower jettison motor shortly after second stage ignition. Any abort thereafter had to be accomplished by using the service module's propulsion system to thrust the spacecraft away from the booster. The launch escape system consisted of 2 major structures. At the top was the forward cylindrical compartment, which housed the 3 solid propellant rocket motors, ballast, the canard system, and the cue ball. The launch escape tower was made of welded titanium tubes. The tower itself served as a method for transmitting the thrust load and positioning the command module a suitable distance away from the hot exhaust of the launch escape motor. The tower was attached to the structural skirt that covered the escape rocket's exhaust nozzles and to the command module by means of 4 explosive bolts. A hard protective cover was attached to the tower, and a soft cover was attached to the command module to help protect the command module, especially the windows, from aerodynamic heating during the boost phase of a normal mission, and also from the rocket exhaust soot. The canards consisted of two wing-like surfaces and a deploying mechanism, which were all part of the Launch Escape System nose cone. The canard surfaces were deployed 11 seconds after an abort was initiated by a piston device which was powered by high-pressure gases generated when two pyrotechnic charges were fired electrically. The canards changed the stability of the Launch Escape System command module. Once deployed, the lift on the canard surfaces caused the configuration to flip end over end so that the command module was stabilized on a blunt end or heat shield forward trajectory. Stabilizing the 5-ton command module in its normal landing direction eliminated the possibility of parachute shroud lines twisting around and being severed by any exposed structure. Now, I want to review the sequence of events for a normal flight of Little Joe 2. First, Apollo Little Joe 2 lifts off at White Sands Missile Range. Second, after reaching the desired test altitude, the abort sequence was initiated by igniting the launch, escape, and pitch control motors. The launch escape motor pulled the Apollo command module to safety. 11 seconds later, the wing-like canards were deployed. Step 4. The aerodynamic forces on the canards changed the stability of the configuration from nose forward to blunt end forward. This caused the vehicle to flip end over end and become stabilized blunt end forward. Fifth step. After stabilizing in a proper heat shield forward direction, the 4 explosive bolts connecting the tower to the command module were activated and the tower jettison motor was ignited. The tower then pulled clear of the command module. Due to the high weight of the command module and its high velocity, the main chutes were not deployed immediately, as the high aerodynamic pressure would just rip them apart in an instant. Instead, a series of chutes were required to provide gradual deceleration. The total weight of all the parachutes used in landing the 5-ton command module was only 54 pounds. The 3 main parachutes, each having 68 shroud lines, meaning each shroud line supported about 50 pounds of the command module weight. Step 6. At an altitude of approximately 24,000 feet, the command module was traveling at about 290 miles per hour. The recovery sequence begins here with the jettison of the apex cover, which houses the parachute compartment. Step 7. 1.6 seconds later, the drogue mortar cartridges are fired to deploy 2 13.7 feet diameter drogue parachutes in a reefed or partially open condition. Step 8. After 8 seconds, the reefing lines were severed by pyrotechnic cutters and the drogue chutes fully open. They decelerate the command module down to a speed of about 160 miles per hour. Step 9. At approximately 10,000 feet, the drogue chutes are released and simultaneously 3 pilot chute mortars are fired. The 7.2-foot diameter pilot parachutes release horizontally in order to extract and deploy the 83-foot diameter main parachutes with minimal interference. To avoid damaging the main parachutes because of excess velocity, they first open to a reefed condition, which further slows the command module down to about 75 miles per hour. Step 10. After 8 seconds, the main chutes are disreefed and allowed to open fully. The speed of the command module reduces to 17 miles per hour for a safe, gentle landing. Now, what happens if only 2 of the main parachutes fully open? In that case, the touchdown velocity will be 22 miles per hour, which is satisfactory and will not harm the capsule or the astronauts. Now let's move on to the flight test. The first flight test for Little Joe 2 was a qualification test carried out on August 28, 1963. It carried a dummy launch escape system, command module, and service module, and was propelled by a cluster of 7 motors, a center-mounted algol surrounded by 6 recruits. The purpose of the qualification test was to check out the basic systems of the Little Joe 2 booster, not the launch escape system. There was no abort capability with this vehicle, and the flight merely attempted to carry the dummy payload through a desired test window where, if everything met approval, the next vehicle would carry a live launch escape system and a boilerplate command module. The Little Joe 2 qualification test vehicle successfully reached the desired transonic abort condition, which was 24,000 feet in altitude, at the proper speed, Mach 1.1, the correct flight path angle, and the correct aerodynamic pressure. Within 3 seconds of successfully passing the test window, a destruct command was given, but nothing happened. The vehicle remained intact and impacted the ground 47,000 feet downrange. The second flight, designated A001, was scheduled to launch on May 13, 1964. This flight would carry a boilerplate command module and live launch escape system to a simulated Saturn V transonic abort. I want to pause here just to make sure everyone understands what a boilerplate is. Boilerplates are research and development vehicles that simulate production spacecraft modules in size, shape, weight, and center of gravity. Each boilerplate has special instrumentation to record flight data for engineering review and evaluation. Boilerplate 12 was used for this flight. Also for this flight, the Little Joe employed a single algol rocket motor ignited at liftoff with 6 smaller recruit motors also ignited to provide extra liftoff thrust. The A001 craft had a total mass of 26,281 kilograms. This was the least powerful and lightest Little Joe 2 configuration flown in the Apollo abort test program. This flight basically was a repeat of the first flight, but this time an actual abort would be initiated as Little Joe passed through the transonic buffeting at an altitude of 4,700 meters. The A001 test flight lifted off at 5:59 a.m. Mountain Standard Time from Pad 36 at White Sands Missile Range. Thrust from the single algol motor was terminated on ground command by rupturing the motor case, and 44 seconds into the flight, the launch escape system fired, pulling BP-12 clear. The boilerplate command module, whose aft heat shield was slightly damaged by recontact with the Little Joe 2 after thrust termination, reached a peak altitude of 4,700 meters before descending back to Earth. The landing sequence proceeded normally until the deployment of the 3 main parachutes. One of the main parachutes ripped away due to excessive swinging of the 5-ton command module. The landing was a success, however, because the Apollo capsule was designed for safe recovery with just 2 parachutes. The third chute, of course, is an additional safety factor. Boilerplate 12 landed 5 minutes and 50 seconds after launch at a speed of 7.9 meters per second, and that was 0.6 meters per second faster than planned, but well within human tolerance. One engineer called it a welcome, unplanned result of the test. As 1964 drew to a close, the Little Joe 2 abort test program at White Sands was nearing its third and in many ways most crucial launch. Because of their fixed fins, the first two solid-fueled rockets had been somewhat erratic in flight. Jack B. Hertz's people at the Convair plant of General Dynamics in San Diego then built a relatively simple attitude control and autopilot system for the rest of their vehicles to allow hydro-pneumatic operation of elevons like ailerons in each of the four fins while in flight. In addition, for the Max-Q and high-altitude abort test upcoming, small reaction control motors were installed in the fin fairings to increase the precision of aiming control to the test points desired. Now we'll move on to the third Little Joe flight, designated A002. The flight was scheduled for December 8, 1964, with 4 recruit and 2 Algol motors. This was the most powerful Little Joe 2 yet flown. The rocket was intended to develop 340,000 pounds of thrust to lift itself and its cargo, which was boilerplate 23 with the launch escape tower, more than 9 kilometers high. The whole assemblage, weighing 41,500 kilometers, was pointed toward the north at a point in space where the launch escape system fitted with canards would pull the capsule and boost protective cover away from the Little Joe while traveling at a speed of Mach 1.5. This area was in the middle of the region where a Saturn V ought to experience Max Q. Now for this flight, Harrison Storms, the Vice President of North American Aviation, you know who I'm talking about, Stormy, flew down to White Sands the night before to observe the launch. When he arrived, he was greeted by a growing army of reporters who were now covering every facet of the program. Roy Neal from NBC, Jules Birdman from ABC, and a couple of dozen others. The press accommodations at the launch site consisted of a row of bleachers and little else, so no one was interested in hanging out with that windswept moonscape any longer than necessary. The reporters asked Storms to give them some kind of guess about the launch time, and he said, "You name it." They laughed, and somebody said, 8 o'clock. They all knew this was a joke. Rockets launches were notorious for delays, and this was the same crowd, after all, that had waited weeks at a time for Storms to drop the X-15. But the next morning, as the second hand swept to the hour, Little Joe roared off the pad, and the reporters turned to Storm in awe. They didn't know he had ordered the countdown started the night before, and since Little Joe was powered by solid-fuel rockets, there was nothing left to do but hit the button. So, at precisely 8 a.m. Mountain Standard Time, on the morning of December 8th, Little Joe 2 roared upward straight and true. 36 seconds later, almost out of sight, and 2 seconds, or 900 meters early, the planned abort took place. After an 11-second coast period, the canards deployed and the capsule tumbled 4 times in its turnaround before stabilizing blunt end forward and jettisoning the escape system. The boost protective cover shattered slightly more than expected, but the 2 drogue parachutes deployed, its 3 main chutes opened, and boilerplate 23 drifted gently to rest 11,000 meters uprange from the launch site after a 7.5-minute flight. Max Q had been higher than predicted, but all else had worked well. Parachute recovery was perfect, thanks in part to the help of the new canard system, which aerodynamically flipped the boilerplate Apollo completely around to its proper heat shield forward attitude. The canards also dampened out the swaying motion before the tower was jettisoned and the drogue chutes were deployed. So at the end of 1964, Little Joe 2, with its payload, was ready for more stringent flight tests. But there was some disappointment as well. The flight testing with the lunar module within the Earth's atmosphere was finally ruled out when Langley discovered in wind tunnel investigations that the combination of Little Joe 2 and the lunar lander would be aerodynamically unstable. Which brings us to the most spectacular of all the Little Joe 2 tests, flight number 4, designated A003. Once again, dozens of newsmen gathered at White Sands Missile Range. The date was May 19, 1965. The mission was an abort test of a boilerplate spacecraft at an altitude of 35,000 meters for a simulated vacuum abort. This time, a total of 6 Algol motors were inside the Little Joe shell. Additionally, this flight was planned to provide the scientists and engineers with their first real chance to prove that the heat shield was adequate in an actual, though not severe, re-entry heating condition. At 6 a.m. that morning, the Little Joe 2 ignited and rammed its payload skyward. A few seconds after liftoff, a fin-vane at the base of the booster stuck and started the 13-meter-tall spacecraft-booster combination spinning like a bullet. 26 seconds into the flight, and still on a true course, the vehicle started coming apart. The abort-sensing system signaled the launch escape tower rocket to fire and pull the spacecraft away at an altitude of 4,000 meters. While newsmen watched the fluttering remains of the Little Joe 2, Boilerplate 22's parachutes lowered it gently to the desert floor. Apollo had another answer. The launch escape system worked in a real abort situation. The reason for the spinning destruction of this Little Joe was that a control system failure locked the fins in a fully deflected position. The vehicle then began spinning so fast about its vertical axis that the centrifugal forces caused it to break up. The engineers were obviously elated to see the launch escape system function so perfectly in a true abort condition, but they had to patiently wait until February 26, 1966 for the first orbital flight of an unrated Saturn in order to qualify the heat shield. Which brings us to the fifth and final mission for the Little Joe 2, designated A004, and scheduled for January 20th, 1966. Although this was the final test in the series, it was the first time Little Joe 2 carried an actual production Apollo spacecraft, command module, and service module. In this flight, Little Joe 2 played the role of a Saturn that had a control system failure which would cause end-over-end tumbling under full power. At 8:15 a.m. Mountain Standard Time, 4 Algol and 5 recruit motors powered Little Joe 2 and spacecraft 002 up to 57,000 feet. A pitch-up maneuver was then begun, and launch escape motor ignition was delayed for 3 seconds to allow enough time for the vehicle to tumble. Then, as designed, the launch vehicle started to tumble. The launch escape system sensed trouble and fired its abort rocket, carrying the command module away from impending disaster. All went well on mission A004. The launch, the test conditions, the telemetry, the spacecraft, and the post-flight analysis. The spacecraft windows did pick up too much soot from the tower jettison motor, but the structure remained intact. Little Joe 2 was honorably retired. Its basic purpose, making sure the launch escape and Earth landing systems could protect the astronauts in either emergency or normal operations, was accomplished. With this successful completion of the SC-002 abort and recovery mission, NASA announced that the astronaut escape system was now officially qualified for use on manned flights. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.